So last time we talked about systems and their properties, and we ended with this idea of being both linear and time invariant. And I'm going to just revisit that and give you another way to interpret linearity and time invariance using block diagrams. So here we go. First of all, linearity can be considered that the system, if it's linear, it commutes with two operations. One of them is a scaling. Okay, so here, interpret that this block diagram like a signal comes in, the arrow points the direction of the processing, and that A with the circle around it means all it's doing is amplifying the signal, multiplying it by A. Okay, very simple process, right? And if it's linear, then it means that if you switch the order of these things, that you get the exact same process. Okay, nothing changed from input to output here. So that's what we'll call commuting. It commutes with a scaling operation. If it's linear, it does two things, right? It commutes with a scaling operation. It also commutes with a sum operation. So here we say, suppose you have two signals coming in, and they get added together. So now that circle with the plus just adds the two signals. And then you process it with H. It goes through the system H. That should be equivalent to doing the H before the summing. Of course, on each input. Okay, so if H behaves such that these commute, then it's linear. All right, so we could say okay. Now, time invariance has a similar sort of block diagram interpretation. Here, if the system commutes with a time delay, and at the time delay could be a time advance. That's just a time delay with a negative delay, right? So time delay or advance. So here we say, let's have this block be a delay by a specified amount of time. And then it goes through your system. So if you want, you can think of it like that thing has some memory and just records the input and outputs it some specified time later. That this should be the same if you do it the other way around. If you process it without the delay and you add the delay afterwards. That means it's time invariant. Okay, so there's kind of a simple way to think about what these two properties meant. Remember, linear and time invariant were the key ones that we're focusing in on. Because when you combine those, what happens if your system is both linear and time invariant? Does anyone remember from the previous lecture? Yeah? Yes, the impulse response, whatever comes out by putting a delta function in, that impulse response tells you everything the system does. And what does the system do in terms of that impulse response? Exactly. The system will always just do a convolution of the input signal with the impulse response. Okay, so let's see one other thing about convolution here using block diagrams. So when we learned about convolution, we noticed that it commutes in a different sort of way. Okay, and that was that x of t convolved with h of t equals h convolved with x. So in this sense, it commutes. Now, if we write a block diagram and try to interpret what that means, it means if you have x of t go into a system, and you know that system is LTI, okay, and out comes y of t. By knowing it's LTI, you know it only does a convolution. So we can specify what the system is by saying it does a convolution with h. Okay, that's what the system does for some h. H defines the system. Well, what's interesting is that that is equivalent to saying something that might seem a little bit weird. If h, this impulse response, was actually a signal coming into a system, and if that system was also still LTI, but a different system, it's a system that does a convolution with x. So I just changed the role of the input signal and the impulse response. Same thing comes out. Still get the same y of t out. So that's kind of a nice way to think of how convolution commutes. You can think of either one as your input and the other one as the impulse response of a system. Okay. By the way, we also have this delta of t convolved with h of t. Now, we worked that out explicitly when we first did convolution. But if we just think of this as an input, if we think of delta as an input to a system, okay, so I'll write it here. Let's say that's an input. And we interpret h. We can choose either one to interpret as the input, and this is the impulse response of the system. Then what would come out of the system? So here we're saying we don't even know, let's say we don't know anything about convolution except what we've just talked about, that it tells you what happens in a system. Well, by definition, I put a delta function into a system. What comes out is, by definition, the impulse response. So we know that has to equal h of t, and great, because we've already seen that before. When we talked about convolution, we noticed that convolving with an impulse response, convolving with the delta function just returns your function. That's the identity operation. So in other words, this interpretation is saying the delta function is your input. The impulse response is h. Of course, what comes out by definition is h. But if we think about it now in the reversed roles, and we say, let's think of h as the input to the system, let's think of delta as the impulse response, then what we see is that a system with impulse response delta is the identity system. Okay, you put h in, you get h out. All right, so that would be the opposite interpretation. Okay, let's do a little exercise to see what happens if we do some time delays in convolution. Now, we already have this idea that convolution is time invariant, and it is. But there's a little bit of some subtlety to that statement, okay? It's time invariant in the sense that if one of your signals is fixed, like the impulse response of the system is fixed, and you shift the other signal, you shift, let's say, x, then the output is just shifted, okay? It's time invariant in that sense. Now, here what I've drawn is two signals, both with a time delay of 3. And I want to convolve them. What will the output be? All right, there's many ways you could arrive at this. We could just explicitly use the convolution integral, which I'll go ahead and do. But does someone have a guess what's going to come out? What's the result of this convolution? What? The original unshifted? Oh, delta with h, which is going to be h. So you're thinking maybe it's h of t. Good. Okay. It's the opposite of what you're thinking. The two delays cancel each other, but it's actually the opposite. Okay. So what? And do we have another guess? Here's one way to think about it. Just think about the fact that it's time invariant with respect to each side of the convolution. So if we have an h of t minus 3, if we know if we convolve that with delta, we just get back h of t minus 3. But delta has been delayed, so that should cause a further delay of 3. Okay, so it's actually going to be h of t minus 6. Whoops, that's not 6. But let's just work it out with the integral. So that was an argument that just used our ideas of time invariance to arrive at it. But let's just plug it in. So we have the integral of delta of tau minus 3 h of, now instead of t, we have to replace t with t minus tau. Okay, just to make this clear. So that's t minus tau minus 3. I just replaced t with t minus tau. Okay, so that's the convolution integral. Now what we should maybe do is use the shifting property, right? So delta occurs at time 3. So this is just going to be h of, and we replace tau with 3. So t minus 3 minus 3. All right, equals h of t minus 6. So there, it's very easy to do convolution with delta functions, okay, because integrals of delta functions are easy. You see, this is shifting. All right, we just plug in tau equals 3. That's the point, right? Okay. All right, so now let's just revisit some of these system properties that we discussed earlier in general. Last time we were talking about system properties. This time, let's say, suppose that the system is LTI and one of those other 4 properties that we discussed. Okay, so for example, if it's LTI and memoryless, then what do we know about it? This is worth thinking about because we already, you should maybe have thought about what it means for the system to be memoryless in general. We've talked about that, gone through some examples. But now let's say if it's LTI, which means it's just doing a convolution, and on top of that it's memoryless, then it should be much simpler to understand. And in fact, it is. It must be just an amplifier, meaning that y of t equals a x of t. That's the most general it can be if it's memoryless and LTI. Okay, so what does that mean? If that's your system, what's the impulse response? Remember, I said it can only do a convolution. So then we should be able to say in terms of the impulse, we should be able to look at an impulse response and say, oh, that's a memoryless system. What would the impulse response of this system be? A times the delta function. How did you know that? What was that? Perfect. So that is the most straightforward way to find an impulse response of a system. You just say, put the impulse function in. Put the delta function in as x, okay, and see what you get for y. You get a delta of t. Now, a more roundabout way, but maybe an intuitive way, is you could just recognize also that this a system like this, when you're used to convolution, you're going to say, oh, I know that that system is just a scaling a times the identity system. Okay, so you might just get that from intuition, but the straightforward way mathematically is always just plug in a delta function to get the impulse response. All right. Just for contrast, you might say, well, aren't all memoryless systems like this? Let's just look at an example of a memoryless system that's not LTI and see that it can be more complicated. So basically, if it's not LTI but it's memoryless, then just just take away the 2 properties, time invariance and the linearity, and you come up with some sort of example like this. What about x of t to the tth power? Okay, so now I'm neither linear because it's taking x to some power. This is not going to be linear. It's also not time invariant. It's got this clock t that's saying what power to raise x to as time goes on. Okay, so as time goes further and further, you're raising x to a higher and higher power. All right. But it is memoryless because at each point in time, the output just depends on the current input. It doesn't matter what happened before or after in x. It just matters what's happening now. So it's memoryless. Okay, so we see that LTI simplifies things. If it is LTI and memoryless, this is all you can have. A delta function at time 0 times some constant. That's your linear system. Okay, that's your memoryless system. What about causal? What do we know about what should the impulse response Can you look at an impulse response and say, yes, that's a causal LTI system, or it's not a causal LTI system? Any ideas? Someone has to have some idea what you would look for to say, if it's causal, then what about the impulse response? Perfect. So the h of t has to be 0 for all t less than 0. So in other words, up to time 0 in the impulse response, there's nothing. At or after time 0, you can have things in the impulse response. Now, the question I get most about this particular property is from students, is they think, isn't that backwards? Shouldn't it be 0 after time for t positive, and the exact opposite of this? And I think the reason they think that is they're thinking you can only depend on the past. The past is negative t, right? But you should think about it this way, one of two ways. The impulse response is what is going to happen when you tap your system. And of course, if it's causal, nothing's going to happen before time 0 if you just wait and tap it at time 0. Okay? So think of the impulse response that way, and you'll see, oh, causal means it has to happen after it's been tapped. Okay? The other way is if you think about convolution and you think about this flip and shift, then you can interpret h as a weighting average. Okay? H is going to say, what kind of weighted average does the system do to your input? But remember, it's a weighted average after reversing in time. Okay, you do a flip and a shift. So in other words, H should be interpreted as an input right now will cause an output this much time later with this much weight. Or equivalently, it should say an output depends on the input t time ago by the weight of H of t. Okay? When you have these interpretations, then causal should be very natural. Why this is what makes it causal. Now let's look at another one here. Can we tell if a system is going to be stable? Of course, we can tell everything about a LTI system by its impulse response. But how would we tell if it's going to be stable? Let's see if we can get some guess. I don't expect you to get this one right, but maybe some guess. Based on H, how would you tell if it's going to be stable? Remember that stable is stable means that if you have a bounded input, that the output is sure to be bounded as well, that you can give some bounds that say if the input's no more than this big ever, the output's no more than some other huge number big. Okay? So what about H would let you know that it's going to be stable in that sense? Delta function's unbounded. Yeah. Oh, so you're wondering how could these memoryless systems be stable? Well, because they are stable, actually. And this memoryless system, is assuming A is a finite number, which it is, then these are always going to be stable. Okay? Because you said something about a delta function, and so clearly you can't just check whether H is bounded, right? Because delta, you have to consider that unbounded. Is there another guess? No. Okay, so the property will be this. If the integral of, what do you think? Integral of what? It's not h of tau, because you can have the integral be 0 and still have some wild stuff going on. The integral of the absolute value of h of t. Okay, so if it's absolutely integrable, if this is less than infinity, then it's stable. Okay. Now, h can be finite, and you can still get an infinite integral here. So let's just check, because this is kind of a fun one to prove. It's actually that this is exactly the condition for it being stable. Okay, so let's just prove it. That means to prove two directions. One direction is to say, if I have this property, then if that's less than infinity, then that implies stable. That's the first direction to prove, right? Because we have a definition for stable. So let's do that. Well, if I have this property, then I can simply look at the absolute value of y, which I'm trying to bound, assuming that absolute value of x is bounded. This absolute value of y equals, just plug in the convolution integral for y, Okay, now that whenever you integrate something, it's less than or equal to, if you move the absolute values inside of the integral, you get something that is at least as big. So if I bring the integral out, now you can, there's a lot of arguments for why that's true. You can convince yourself that's true by thinking of an integral as a sum. Okay, if you sum a bunch of numbers and then take the absolute value, you'll get something at least as large by doing the absolute values first. Could be bigger because the sum can cancel parts, right? Okay, so so if you do this, that's at least as big. And then you say, well, now I have an absolute value of two things multiplied that is less than, well, that's equal to the absolute value of each one multiplied. But in particular, it's less than or equal to absolute value of h of tau times our bound on the absolute value of x. We know x is never bigger than this number, b of x. All right, so, and then that just comes out, right? And so that equals b of x times this integral, which is exactly what we said. If that's finite, then you're in good shape because this whole thing becomes your bound. You're bound on y. This is the bound b of y. Okay, so we see that direction, that if you can integrate the absolute value, that it's stable. Now the other direction is we should come up with an example. So now we want to prove that if it's stable, that implies that this has to be finite. And that we're going to do by contradiction. So that means what we're actually going to do is do the opposite. We're going to say if this is infinity, I'm going to show that it's unstable. Okay. So that'll prove that same statement. So I'm going to say, sorry, well, like Buzz Lightyear. Okay. And so we're going to say that. So we're going to assume that this is infinity. And we're going to choose an input that shows it's unstable. So let x of t equal the sine of h of negative t. Okay, now what is sine? This is not sinusoid. So the sine is just very straightforward. It's just telling you whether the argument is positive or negative. So the sine of anything, z, equals 1 if z is greater than 0, negative 1 if z is less than or equal to 0. Okay, so in other words, x is always going to be plus or minus 1. It's just going to track h. It's just going to be the same sign as h, but it's always going to be plus or minus 1. All right? So, so notice, of course, that x is bounded, right? Absolute value of x equals 1. I'll say it's less than or equal to 1. So it's bounded for all time. But what's going to happen when you put this through your system? In particular, let's look at time 0. Okay, I don't know. We're going to get a whole signal out. But let's look at that signal at time 0. And I'm going to show you that it blows up at time 0. Okay, so let's just say h of, well, we know that h of t is this convolution, right? So h of t is this thing. And we just want to look at h at time 0 to show that at least at one point in time it's extremely large, actually infinite. Okay? And so that means plug in 0 for t. So it should be h of tau x of negative tau. You see that? Because I just plugged in 0 for t. All right? Now, because of our definition of x, this just becomes, notice, this equals h of tau sine of h of tau, the negative t, there's a negative tau there, and in the definition, okay? And that equals the absolute value of h. Equals infinity. Okay, so there we've given an example of how you can make this thing blow. It's kind of a very instructive example. It says, oh, if you have some h that doesn't sum absolutely, you see how you can get an input signal that just, kind of collects all of the impulse response just coherently at one point and makes it, you have a very big output. Okay, there was one more property that was invertible. And there is a nice way to check whether a signal is invertible, but this I will leave so that you can think about it. In fact, even just after this lecture, you should have a good understanding. Come back to this question, see if you can answer it. Because we're going to understand something very nice about convolution. That's what we're doing right now. So far, in the previous lecture, we connected together these system properties with convolution. And we said, why is convolution special? Why should we care about it? Well, now we're going to connect other things you've learned so far to that same topic. So that we're going to connect to the Fourier transform. Okay, so consider a convolution. Let h of t equal x of t convolved with h of t, okay? And let's just define that the Fourier transform of x is capital X of f. Fourier transform of h, we'll call that capital H. We're just keeping things general. This is just to represent some arbitrary x, some arbitrary h, and their Fourier transforms. Now, what I want to show you is that the Fourier transform of y can be computed very easily from the Fourier transforms of x and h. So what we're going to do now is one of the very key things that we'll remember from this entire course material, because it's it's the most important property of the Fourier transform from our perspective. All right, let's just plug in the Fourier transform integral to y of t. That's by definition. Okay, we should be able to plug in this integral. And we see that, so this is the definition. Next, we're going to replace y with its definition under convolution, right? So by definition, we have y is a convolution. So we do the substitution here, we'll get another integral, the convolution integral. And now the rest of our outer integral here. Okay, so we need to somehow do this integral. Well, conveniently, let's do these in the opposite order. So we're going to switch these. Of course, you can't tell I switched them because they're over the same limits here. But we're going to switch them by moving the d tau and dt. So keep this the same. But what we're going to do, oh, actually, no, I'm going to bring, okay, it'll be more clear. I'm bringing the x of tau and the d tau out of this integral. I'm going to integrate with respect to t on the inside here. So bring x of tau out of that integral. And here I'm going to do the integral with respect to t. So I have to leave everything that has a t in it. Okay. And then I had a d tau. I like to put that at the end. Okay, so just change the order, right? Now, to do this, I should do a substitution, right? I should do something like tau prime equals t minus tau, so that I can get rid of that. So that equals the integral of x of tau, integral of h of tau prime, e to the negative I 2 pi f, and then replace t with tau plus tau prime. By the way, if you're not, I realize that some people may not be used to using tau prime as just a variable. Okay, that's just a variable. It's a new name. It doesn't mean derivative or anything. All right. And this is with respect to tau prime. Now, okay, so here's just the U substitution rules, right? Now, notice that this exponential function splits into two parts, a product of two parts, and one of those does not depend on tau prime. So what I'm going to do is move the part that doesn't depend on tau prime out of that integral. So it's going to be e to the negative I 2 pi tau. Whoops, I should have a, f tau. And then I have the rest of this integral. Okay. Now, I'm going to also move. So you see what I did. I took out the tau out of this exponent. I split it into a product of two parts and just yanked it out of the integral. One more thing. I'm going to just write this over here. In fact, I'll just erase that. It's just a matter of how we write things. Because notice that this, I guess the key here, I should leave that there. The key is this inner thing here, this whole function now, doesn't have tau in it anywhere. It did before, but I removed everything that had tau in it. So now this is just a function of f and nothing else. So that's why it's valid for me to move this inside. Okay? So that means that, in other words, I just took out that constant part, constant with respect to tau, and I get two separate integrals multiplied together. Okay, and hopefully someone recognizes what's so simple about this. What do we have? What's the final step? Yeah, I'm hearing it. So this is a product of x of f and h of f. Those are I'm just identifying those two. This is the Fourier transform of x right here and the Fourier transform of h. Okay, so nice in the end to see what we have. We have that the Fourier transform of the output is exactly just the product. What could be simpler? Products are so easy, right? Now, this isn't a convolution or anything complicated. It's just a product of the two Fourier transforms of the input signals to the convolution. So let me summarize that convolution property here. Okay, so the convolution property says if x of t convolved with h of t, that the convolution of two signals, when you take the Fourier transform, it's just the product of their Fourier transforms. Okay, an equivalent way of saying this is that the Fourier transform, this is just an equivalent way with different notation for that same property. That equals the Fourier transform of x of t times the Fourier transform of h of t. Okay, by the way, same property holds in discrete time. So you could go through the exact same derivation with sums. So this property is for both discrete time and continuous time Fourier transform. And like I said, it's our most important property of the Fourier transform. Let's try to internalize what this is really saying. So what it means is that, here, let me write that it's the most important. I mean, up to this point, we have used the Fourier transform for signal analysis, like Shazam is a signal analysis example. It doesn't, these properties of the Fourier transform are not, it's not immediately obvious that they're even important for doing something like Shazam. The goal of signal analysis is transform your information into a way, usually you want it to be somehow sparse. You saw in music that there are points in the music that have high energy and most other points don't have high energy. So in some sense, it becomes kind of sparse once you do a Fourier transform. And you can use that sparsity, the fact that most of your signal exists at certain points, to fingerprint it and do all sorts of things. Okay, so that's one reason to use a transform. But now we're getting, in the first couple weeks, I even showed you there are many transforms that might give you sparsity, might have certain purposes. Now, what we're seeing now is actually the extra reason why the Fourier transform is so important, why it comes up in so many fields. It's because of this convolution property. Because one way to think about this is that, and this is using linear algebra jargon, so it diagonalizes an LTI system. Okay, so this is, so let me just explain for a moment. So this is a concept from linear algebra. But really what it means is that convolution, which is somewhat complicated, you can gain some intuition for it, but actually calculating convolution is a bit involved, right? And any LTI system is doing some sort of convolution. But what this is saying is that if you transform the space you're looking at, go to the frequency domain instead, then it's always simple. Any system cannot do anything more than just scale different frequencies by different amounts. It's always going to be very simple. Now, the notion of diagonalization in linear algebra says, look, if you have a general linear system, and of course that's what the L means in LTI, so these are linear systems. They're more constrained than general linear systems, but in general, you have like a vector multiplied by a matrix. That matrix defines a linear system. Linear systems can do complicated things, and it may be hard to interpret how a vector gets affected by a matrix, by a linear system. But if you diagonalize, okay, that tells you reorient your vector space in just the right way, then it will no longer do anything complicated. All the linear system can do is rescale each axis. That's all it can do, okay, once you've diagonalized. It's multiplication, and that's exactly what we're seeing here. So this truly is the same property. It's saying that any LTI system is diagonalized by the Fourier transform. So if you ever have a purpose to look at something that's linear and time invariant, the Fourier transform is going to be the right transform for understanding what it does. Okay, so let's try to make that even slightly more concrete. Let's say you have x of t goes into an LTI system, which we said is always going to be a convolution, and out comes y of t. It's just a convolution of x of t and h of t. Well, now what we're saying is, if we instead think about it in the frequency domain, it'll be easier to interpret what this system does. What I mean by that is, the frequency domain means for every signal, consider instead its Fourier transform. We know that that's all the information is there. It's an invertible transform. So think of what the signal that comes in terms of its Fourier transform. And we know that the LTI system then is nothing more than basically a frequency selective amplifier, right? It'll just have an h of f, and all that's going to happen is what comes out is the input times h of f. Okay, that's all that can happen. So that leads to this notion of filtering, which is one of the buzzwords of like signal processing, of the material in this class. And that would be that you can design an LTI system to perform some sort of course, any LTI system is just going to be multiplication in the frequency domain. So design the system H to have some desired behavior. Of course, a desired effect on the frequency domain. So the filter behavior will be best interpreted in frequency domain. All right. So an example would be this. Suppose we want. You might have something in mind of what you want your system to do in terms of frequency. So like you might want what's known as a low-pass filter. Low-pass filter, and generally a low-pass filter means that its h of f will kind of allow low frequencies to pass more than high frequencies. Maybe it has some cutoff frequency, fc, and you can see that if h of f is this shape, when you multiply it by x, things above the cutoff frequency will disappear, and you'll keep things in low frequency. So this is a low-pass filter. And how would you implement a low-pass filter? Well, to implement, you're going to do a convolution. So you should take h of t as the inverse Fourier transform of h of f. Whatever you designed, that's one way to do it. You have an h of t. If you can do a convolution in time, that's going to implement your filter. Okay, let's look at another. Let's look at some more specific examples with actual formulas. So suppose that, yeah? Yeah, if it was not symmetric, then it means that in time you're not going to have a real signal. Because being real in time translates to having symmetry in frequency. Yeah, and we'll discuss that more. Good thinking, though. All right. So suppose that we look at the example we've talked about so many times when we discuss convolution. Take a local average. Okay, we talked about this even the very first day of class. Said, well, if you want to smooth a system, one idea, smooth a signal, one idea is just let y of t be a local average. So here's the formula for. Well, the sound went out for some reason for the last few minutes of this lecture, so I'm just going to add a brief explanation of what I was explaining. So what we're doing as an example here is a local window averaging, and here I give the expression for how you would calculate a local average of width w of a signal x. And first of all, you should realize that local averaging is linear time invariant. That's something we've mentioned several times. Because it is, it's going to be doing simply a convolution between the input signal and some impulse response h. Now, what is the impulse response? What is h? You can tell, for one thing, when you're familiar with convolution, you can tell that just by inspection, you might be able to notice that the impulse response is 1 over w times a rect function of width w. Okay, but even without the intuition of how to just observe that by inspection, you always have a plug-in method to figure out what the impulse response is, because by definition, the impulse response is what comes out when you put a delta function into your system. So here we see that you plug in a delta function and into the integral that defines this system, and you get exactly what we said, 1 over w times a rect. To do that, you have to know how do you compute the integral of a delta function over a finite interval. We haven't specifically talked about that. We'll go over that next time. But you could probably see, you probably just have some intuition that it's going to be what I claim it is, this rect function. Okay, so what does that mean in the frequency domain? What is this process doing, this local averaging? If we view it as a filter, well, we need to take the Fourier transform of h. And we know what the Fourier transform of a rect function is. So we use linearity, pull the 1 over w out of the Fourier transform, use our property of time scaling, and we get to a w and a 1 over w term that cancel out, and we find that the Fourier transform is just sinc of wf.
here I've plotted it. We see that has a value of 1 near low frequencies, 0 around 0 frequency. And in particular, we know what sinc function looks like, but it hits 0 at certain points, 1 over W, 2 over W, and so forth in frequency. Because of what we understand about filtering, we know that this convolution is going to be multiplying the Fourier transform of x by this filter, this h of f. So that means those frequencies, the 1 over W, 2 over W, 3 over W, those frequencies will be completely eliminated by doing this local averaging. Now, you could have observed that just by trying it out. Put a sinusoid as x, and you'll see that when you do an average over this window, you'll integrate over exactly a period of the sinusoid, or an integer, a multiple of the period, and that will give you 0. So you'll eliminate certain frequencies entirely. More importantly, though, notice that the shape of sinc tapers off at higher frequencies. And so that is the large picture of what's going on when you do this smoothing. You're reducing high frequencies to some degree, okay? Because the sinc function has this 1 over f in it. So the high frequencies will be attenuated. One thing I want to mention, of course, there are parts of the sinc function that are negative, and so you'll multiply by a negative number. In some sense, that's not too important. What's important kind of is the magnitude of these frequencies to understand intuitively what happens when you multiply the h of f times x of f. Okay, so lastly, and I do want to do another example. We ran out of time in this lecture. The other example would be the ideal low-pass filter. We'll do it next time. But I want to point out that sometimes it's actually faster to compute the inverse Fourier transform of the product of Fourier transforms. In other words, use the Fourier transform to do convolution rather than doing it directly as we've defined convolution as an integral. So when I say sometimes it's faster to do it indirectly through the Fourier transform, I mean that in two different ways. It could be faster analytically on paper, okay, if you're trying to calculate explicitly what is the formula for some convolution. Sometimes it's faster to do the Fourier transforms, multiply, do the inverse Fourier transform. But even maybe more importantly for technology, this can be faster in real time, in real signals on computer. Using the FFT, you can do a multiplication and an inverse FFT sometimes faster than if you just explicitly calculate out the sum that a convolution states. So think about the fact that if your signal x and your impulse response h are similar in length, convolution, let's say that length is n, convolution will be an order of n squared because of all the multiplies you have to do. Okay, but the FFT we know is order n log n. So if you do n log n, once to x, once to h, then you do a multiply. Well, multiplying two signals is just order n. And then you do an inverse FFT, which again is order n log n. The combination of all that can be much faster than convolution directly. And that's significant for signal processing. You can actually use the FFT in your signal processing algorithm.